Today, we are going to break down one of the most fundamental, most important building blocks in all of modern electronics, the diode. You can think of it as the ultimate traffic cop for electricity. It looks simple, right? But it has this surprisingly complex and absolutely crucial job, making sure that current only flows one way.
Okay, so here's our game plan. We're going to start with the really simple idea of a one-way valve. Then we'll build on that with a perfect, what we call an ideal model. After that, we'll see how to actually analyze circuits with it, compare that perfect model to how things work in the real world, and then finally, we'll peek inside the diode itself to see the physics that makes it all tick.
So what is a diode really for? I mean, what's its whole purpose? Before we get into any of the complicated electronics, let's start with a really simple analogy just to get our heads around the basic idea.
I want you to picture a valve in a water pipe. You know, one of those with a little flap. It lets water flow forward, no problem. But if that water tries to flow backward, the flap just slams shut and the flow stops, dead in its tracks. Well, a diode does the exact same thing, but for electric current. It's all about controlling direction.
So this directional behavior, that's what defines a diode. It has two connection points, two terminals. The inside, where current is allowed to enter, we call that the anode, and the outside, that's the cathode. The easiest way to remember it is to look at the symbol. That little arrow points in the direction that current is allowed to flow. Simple as that.
Now here's the thing. Real diodes, they're kind of complicated. So to make life easier when we're analyzing circuits, engineers start with this perfect, imaginary version. We call it the ideal diode and, well, it has a bit of a split personality.
This model simplifies everything by basically pretending the diode only has two possible states. It's either a perfect conductor, letting all the current through just like a closed switch, or it's a perfect insulator, blocking all the current like an open switch. On or off. That's it.
And this split personality has specific names. When we apply voltage in the direction the diode allows, we say it's forward biased. In our perfect little model, this just means it becomes a closed switch, a short circuit with zero resistance at all. But if we try to push voltage the wrong way, it becomes reverse biased, and now it acts like an open switch that completely blocks any current from flowing.
Okay, so how do we actually use this thing? Well, with this simple model of open and closed switches, we can actually analyze some pretty complex-looking circuits using a surprisingly simple four-step method. And here's the wild part. The very first step, it's not some crazy hard equation. You just, well, you guess. Seriously, you look at the circuit and you make an educated guess for each diode. Is it on or is it off?
This is the entire process, right here. First, you assume the state of every diode in the circuit. Second, you enforce those assumptions. You actually redraw the circuit, swapping in short circuits for the on diodes and open circuits for the off ones. Third, you analyze that new, much simpler circuit. And fourth, and this is the most important step, you check. You have to see if your results make sense. Like, if you assumed a diode was on, did your math actually show current flowing the right way through it? And this is the golden rule. You have to remember this. If even one of your assumptions turns out to be wrong, let's say you calculated a negative current for a diode you said was on, your whole solution is junk. It's invalid. You can't just fix that one part. You have to throw the whole thing out, go back to step one with a new guess, and start the analysis all over again.
Look, that ideal model is a fantastic tool. It's great for learning, great for quick, back-of-the-napkin calculations. But you knew there was a but, right? Real diodes are not perfect. So let's look at a spectrum of models that get us closer and closer to reality.
In the real world, a diode isn't a perfect switch. It has what we call nonlinear behavior. That sounds complicated, but all it really means is that its response isn't a simple straight line. A tiny, tiny change in voltage can cause a huge change in current. And to capture that, we need more detailed models. Models that account for things like the small voltage it takes to actually turn the diode on.
This table basically shows how we can layer on the realism. The first approximation, that's our ideal switch we've been using. The second is a lot more common. It adds a tiny 0.7 volt hurdle. Just think of it like a small price you have to pay. You have to spend 0.7 volts just to get a normal silicon diode to turn on. Then there's the third approximation. It's even more precise, adding a small resistor to account for the diode's own internal resistance. So the key thing to take away here is that you don't always need the most complicated model. That tiny internal bulk resistance from our third model, it really only matters if the other resistances in your circuit are also super small. If they're not, that little bit of resistance is just a drop in the bucket. You can usually just ignore it.
Okay, so we know how a diode acts, but why? Why does it have this bizarre one-way property? To answer that, we have to zoom way, way in and look at the physics of what's called a p-n junction.
So at its heart, a diode is made by mashing two slightly different types of silicone together, a p-type and an n-type. Don't worry about the names. Just know that where they meet, they naturally create a little barrier that stops current from flowing. We call this the depletion region. The magic happens when we apply an outside voltage, because that voltage can either shrink this barrier down or make it even bigger.
And this image shows you exactly what's happening to that barrier. When we're in forward bias, our external voltage is literally pushing against the barrier, shrinking that depletion region and letting the current flow right through. But in reverse bias, the external voltage actually helps the barrier. It pulls it wider, making it even harder for current to get across. It's like making a dam bigger to stop more water.
So, at the end of the day, all this physics is what creates the behavior we've been talking about. Lowering that barrier is the real-world version of closing a switch. Increasing the barrier is what opens that switch. Our whole simple switch model, it's really just a convenient shorthand for what's physically happening right here.
This graph, plotting voltage versus current, is the perfect summary of everything we've talked about. Just look at the right side, you apply a little bit of positive forward voltage, and whoosh, the current just shoots straight up. But now look at the left side. You apply a negative reverse voltage, and you get pretty much nothing. Almost zero current gets through. That is the one-way valve, visualized on a graph. So what's the big takeaway from all this? It's really about the power of using models in engineering. We start with a perfectly simple idea, that ideal switch, just so we can understand the main job of the component. Then we strategically add layers of complexity, like that 0.7 volt drop, but only when we need more accuracy to solve a real-world problem. And this leaves us with a final thought to chew on. These models, these simplifications, are what make designing complex electronics even possible. But it brings up a bigger question, one that goes way beyond circuits. How do we decide when a simple model is good enough for the job, and when do we have to finally ditch it and embrace the messy, non-linear details of reality?